So let's move on and talk further on the single slit. Intensity has a central maximum at theta is equal to 0. And other secondary maximum at theta is approx of n plus half into lambda divided by a. And next a minimum at theta is equal to n lambda divided by a. Over here where n is equal to plus or minus 1, plus or minus 2 and plus or minus 3. It is easy to see why it has a minima at these values of angle. Consider first the angle theta, where the path difference a theta is lambda, then theta is equal to lambda divided by a. Now divide the slit into two equal halves, Lm and Mn, each of size a divided by 2. For every point M1 in Lm, there is a point M2 in Mn, such that M1 M2 is equal to a divided by 2. The path difference between M1 and M2 at P is equal to M2P and M1P. So it's subtraction, which is nothing but theta into a divided by 2. So that's your lambda divided by 2 for the angle chosen. This means the contributions from M1, M2 are 180 degree out of phase and cancel in the direction. That's why your theta is equal to lambda divided by a. Contributions from the two halves of the slit Lm, Mn therefore cancel each other. So theta is equal to lambda divided by a gives the angle at which the intensity falls to 0. One can similarly show that the intensity is 0 for theta is equal to n lambda divided by a, with n being any integer. Notice that the angular size of the central maximum increases when the slit width decreases. It is also easy to see why they are maxima at theta, that's n plus half lambda by a, and why they go on becoming weaker and weaker with increasing n. Consider an angle theta is equal to 3 into lambda divided by 2a, which is midway between two of the dark fringes. Divide the slit into three parts. If we take the first 2/3 of the slit, the path difference between the two ends would be 2a by 3 into 3 lambda by 2a, which is equal to, obviously, it's lambda. The first 2/3 of the slit can therefore be divided into two halves, which have a lambda by 2 path difference. The contribution of these two halves cancel in the same manner as described earlier. Only the remaining 1/3 of the slit contributes the intensity at a point between the two minima. Clearly, this must be much weaker than the central maximum. One can similarly show that there are maxima at n plus half theta by a with n is equal to 2, 3. Here is the single slit experiment. So here is a diffraction pattern, and you are able to see the bright fringes and a dark fringes. So obviously these become weaker with the increasing n, since only 1/5 to 1/7 of the slit contributes in these three cases. The photograph and intensity pattern corresponding to it is shown here. There have been prolonged discussion about the difference between interferences and diffraction among scientists since the discovery of this phenomena. So, in this context, it is interesting to note that what Richard Feynman has said in his famous Feynman lectures on physics. This is the one. This is called as Feynman lectures related to physics. No one has ever been able to determine or define the difference between interference and diffraction satisfactorily. The best we can do is, roughly speaking, is to say that when there are only a few sources, say two interfering sources, then the result is usually called interference. But if there is a large number of them, it seems that the word diffraction is more often used.